Okay, I'm coughing a little. Hopefully this doesn't get too bad. Um, but I'm stopping. Let's see. Came back to our definition of electric flux, and we talked about what it means and how to sort of practically use it. I want to make sure we're not losing the forest for the trees here, because I want to make sure we remember what the point of all this was. So we got back to how this works with the vacuum cleaner flow, and we were originally talking. Let me see if I have it up here. Yeah, we were originally talking about how you could draw a boundary around a bunch of charges and then calculate the entire electric flux through this entire closed surface. And you'd have to imagine this is a closed surface, not just a line, but an actual closed, surface covering this in 3D, so it goes above and below these charges as well. Count the whole electric flux through it, and that would give you something proportional to the total charge inside. So remember, we found out that you can count the number of field lines through these guys and find out the total charge inside, right, if you're just doing an electric field diagram. And we thought about how this is similar to airflow coming out of vacuum cleaner hoses and being sucked in by other vacuum cleaners. And so then we thought, well, if you wrap a surface around some of these hose ends and you count all the air going in and out of the surface, like a big window, with that faces in all directions, and then you can count all the air going through it. Then you could figure out how many hoses are inside and how much they're sucking or blowing. So the idea we're trying to get to down here is that if you take a closed surface, and so this is actually what Gauss's law is, almost. So let me make sure I've got a brush, and Gauss's law, almost, parentheses there, Gauss's law, almost, wow, that is a horrible W. So let's try, that's a little better, at least it's more of a W. Gauss's law almost says that, is my handwriting this bad on the board? God, I hope not. All right. Says if you wrap a closed surface here, and you take the total flux through a closed surface, surfacey, no, just surface. Total flux through a closed surface. Actually, I don't want to have that. Excuse me. I apologize if this is loud. I'll try not to cough while I'm recording. So, capital Phi electric flux. And this is total electric flux. And so the idea is that Gauss's law says that the total flux through this closed surface should be equal to, somehow proportional to, so I want to make this equal to some constant C, capital C, times the charge enclosed. Okay, so C is some constant. Phi sub E is the total flux through the closed surface, and Q enclosed is, of course, the total charge inside. So the idea is you wrap a surface around a bunch of charge, take the flux through the entire surface, all around, the whole surface wrapped all the way around the thing, front, back, top, left, bottom, right, all of it. Take the total flux, and that will be proportional somehow, some constant that is the same everywhere for all things, to the enclosed charge. So, what is that constant C? What is that constant capital C? So what I want to do is I want to do one case where we already know the answer, the simplest possible case, and use that to find this constant c. Now, you might be looking at this and thinking, wow, he drew this little abstract, sort of deformed blob type shape, and if I even want to be really awesome, I'll try to shade it in. That just makes it worse. Whatever. Okay, and so it's this 3D shape that could have any arbitrary blobby shape, and somehow you've got to find, what this is over the entire surface, but it's not going to be. This isn't going to be the same everywhere, right? You can only use this if E dot n hat is the same over the entire surface. So then we have to break it up into other little surfaces and do this, and you think this is going to be horrible, especially because usually this is expressed in terms of calculus. And so you think this is going to be horrible. Well, in a sense, it is horrible, but the result of the horribleness is that you can only do it really at all in a few very specific, very simple situations. And so the good news is that we only do those simple situations, and it's actually not horrible in the simple situations. It actually turns out to be pretty easy. So what I want to do, I've already set up, oh no, I haven't, whoops, okay. So I want to set up, just copy this down here and move down, and this is going to be our little reference. I want to take the very simplest case, which is just going to be a point charge. So here we go. Let's see. Okay, so simplest case, point charge Q at the origin. Okay, so here now, let's see if I can draw this right. So we're going to say here's our origin, and here I'm just going to do it in green is our point charge Q. Okay, so we want to talk about what the electric field is. Remember, we're doing electric flux here, so we want to set up a we want to talk about what the electric field is here at this point. Now, I could set up coordinate axes. For example, I could go, here's, let's call this, let's say this is X, this is Y, and this is Z, okay? And I want to talk about a specific point here, which is R, okay? Or, you could even say there's a vector leading out to our position vector leading out to this point from the origin, okay? And then I want to find what the electric field here is. E here, okay? So, and bear with me here for a little bit because, in fact, I'm just going to erase the here part. Bear with me a little bit and you'll see where this is going. So, the electric field here, first of all, let's think about which direction the electric field might point. Now, again, we already know the answer to this. We know the electric field around a point charge. And so just because you know the answer, don't immediately yell it out. Let's pretend, I mean, you're probably alone, but whatever. Let's pretend we don't know it yet. We want to find what the electric field is here. So the first thing we know is, well, let's look at symmetry. Can the electric field be going, say, up like this? Does that really make sense? Well, if it's going up like that, that kind of implies that you could turn it in a different direction, like you turn this whole problem and have it be going like that, for example, or have it be going like in the direction of the z-axis. So if you see what I'm saying, you think about the symmetry of the situation. The symmetry means if you are at this point, all you really know about is this charge Q here, and there's no reason to think that the field should go this way or this way or this way specifically. The only directions you'd expect it to go are maybe out or maybe in, okay? So the electric field might possibly go outward, like directly away from Q, or it might possibly go directly inward. Anything else doesn't really make sense by symmetry, okay? So first we can say by symmetry, and let me just make it clear this little thing here is just our walled off reference point. Okay, by symmetry, and now I've lost that exact color purple, so this might not be the same. Symmetry, we can say that the electric field, what do we know about it? It has to point along the radius direction, okay? And if we think about this, the easiest way to express that is in terms of a unit vector. So here's our r vector. R hat is going to be a unit vector pointing in the direction of r. And the electric field has to point in the direction of r hat, okay? And it has to have, and it can have a magnitude. It can have a positive or negative magnitude, so it could point in the negative r hat direction. So what I'm going to say is it has some scalar-ish value e, which could be it's the magnitude plus possibly negative, okay? And that is a function of r. Let me see if I can draw that parentheses a little better. So this might change with r. E might change with r, but it has to depend on r. And so the fact that it also changes with r, again, comes from symmetry. If you're this far away and the electric field is pointing away with such and such a strength, you'd expect to see the same behavior at any point that's also that far away. So if that's your r is pointing that way, you'd expect also, say down here, well, I'm not connecting these exactly, but say down here, if that's your r, you'd expect the electric field to also be pointing straight away, right? So this is really the only kind of field that makes sense with the symmetry, okay? So remember, this E of r is a scalar, and what we're saying is that the electric field vector can only point in the r direction or opposite to it, okay? So that sort of narrows down our possibilities, okay? Now what we need to do is we need to pick a surface to find the flux on, okay? This is where it gets a little tricky. Not very tricky, though. Remember, we are looking for places where we're looking for surfaces we can draw to enclose this Q, some surface we can wrap this Q in that will keep this E dot n hat constant. Okay? So, n hat, remember, is always going to point perpendicular to the surface. It's always going to point out from the surface. And we want this dot product with E hat, not with E hat, with E to be constant. So we scroll up a bit and we look at our ways for E dot n hat to be constant. First way is to have zero electric field. Now that's straight out here because we know that's not true. Okay, so we can't deal with that. Second way, actually I'm going to go to the third way. The third way is to have the electric field vector be parallel to the surface. Now that's kind of hard down here because the electric field vector is always going out from Q, right? It's always going out from the origin, which means if you're going to pick a surface that this electric field is parallel to, then that surface has to slice through the origin somehow, right? Or it has to be pointing like end on at the origin, like it has to have one of its edges pointing at the origin. So that doesn't work so well either, okay? So 1 and 3 are out. 2, electric field perpendicular to the surface with a constant magnitude. Okay, remember this is what it means. Electric field vector has to be perpendicular to the surface, and the electric field itself needs to have a constant magnitude. So first of all, let's look what kind of surface can we pick where the electric field that we have identified here as being of this form, right? This has to have a constant magnitude. Okay, well, r hat has a magnitude of 1, so let's not worry about that. What we need is a surface where E, this scalar E, is constant. Well, the easiest way, right? I mean, if E changes with r, the easiest surface to pick is a surface where this r distance is always the same. This scalar r distance is always the same, right? So to make it clear, this r here, remember this is a scalar r. This is just a, depending on the distance from the origin, okay? So if we pick a surface where this r is always the same, then we will have our magic surface where E dot n hat is always constant. And what kind of surface has always the same distance from some point? That's a sphere. So what we're going to do is our surface is going to be a sphere of radius r, more or less. That's a horrible sphere, okay? So our Gaussian surface, not Gaussian surface, sorry. Make an A, come on. Gaussian surface. Gaussian is like an adjective, but I'm just going to call it a Gauss surface, okay? Gauss surface sphere Speary, nice. Jeez. Maybe having an ear infection destroys your spelling. Sphere of, come on, radius r centered on the origin. Okay, and so now we take, so we just want to evaluate this, right, over the whole sphere. And this is actually a very easy one. Okay, so now at any point on the sphere, let's see, say at this position r we've identified here, what direction does the n hat vector point? Well, it points straight out from the center, right? So in fact, in this case, n hat points the same direction as r hat, right? Because at any point, r hat is a unit vector pointing the direction of the vector from the center to the surface, and that is also the direction that goes straight outwards, and that's the way n hat points. So the answer, well, I'm just sort of writing 1, 2, 3 for our steps. Now we know that n hat equals r hat on the sphere. So therefore, E dot n hat equals, well, it equals E dot r hat, right? Or it's easy just to say, look, let's just plug everything in it now. So here's our E vector, right? So E, which is a function of r, okay, times r hat, okay, this is our E here. We dot that with n hat, and that's pretty easy because, so I'm going to go down just this far. There we go. Just get a little more room. Okay, that's pretty easy because this is a scalar here, so that moves out. And r hat dot n hat, well, these are two unit vectors pointing the same direction. In fact, they are the same vector. So their magnitude, or the dot product of them, is just the square of their magnitude, which is 1. So easy enough. So this product here, this product in here, in this case, this is it, is just this. E, this scalar E, which is a function of r. The electric field points outward everywhere with some dependence on r. We don't know what that is, okay, and we're going to get there, okay, and that is what our, we call it flux per unit of area is, okay. So let's go now to, I'll do step 4 in, let's do green. I haven't really used green yet. So now step 4 is, I'm going to say the electric flux here is equal to the whole area of the sphere, the entire surface area of the sphere, times this E dot n hat product. Okay, well, so let's evaluate that. What is the surface area of a sphere? The surface area of the sphere is 4 pi times the radius squared. And this is a sphere of radius r. So 4 pi r squared is our area. Okay, I'm going to parenthesize that. And then this E dot n hat product is this E of r. We found that up here, right? This here, okay. So E of r. E, which is a function of r, I'm saying. Not E times r. Okay, and so now we get that the electric flux through this entire surface of radius r, the entire sphere of radius r, is 4 pi squared, no, it's not pi squared, just 4 pi r squared times whatever the magnitude of the electric field r away from this point is. Okay, so now this is the flux through this sphere for this unknown electric field due to a point charge. Now, as I said before, we do know the electric field due to a point charge. We've done this, but I want to show you how this leads into Gauss's law. So that's our electric flux there. Now, remember up here, we had that the electric field, or the electric flux over an entire closed surface was going to be equal to some constant c times the total enclosed charge. Well, here it is, right? So I'm going to say this here is I'm going to copy down what I had before, equals some constant c times our total enclosed charge. And in this case, our enclosed charge is just this charge Q up here, right? So I'm just going to put that charge Q in there. Okay, so this is our phi E here. I'm going to go with 4 pi r squared E of r equals C times Q. Okay, and so then if we want to find the electric field, we say our electric field, which is a function of r, is C times Q over 4 pi r squared. Okay, this is the point where we bring in what we actually know. And what we actually know, and I'm going to write this in blue, so we already know Coulomb's law. Coulomb's law. Okay. Coulomb's law says the electric field around a point charge is kq over r squared times r hat. Now, we know now that our electric field magnitude around this point charge from Gauss's law is this. And so if we want to put, if we want to make it a vector version, we just do that and put the r hat on it, right? Because previously up here we said the electric field is going to just have this radial magnitude and then multiply that by r hat. So now we're back to here, and now we take these two versions, Coulomb's law, the Coulomb's law version. So this is, oops, this is the Coulomb's law version, and this is the Gauss's law version, and we set them equal. Okay, so moving on down one more. These are going to be equal, so I'll do these in red. Why not? And we get CQ over 4 pi r squared r hat equals KQ over r squared r hat. Okay, so canceling color. Let's go with purple as a canceling color. So the r hat goes away, and the r squared goes away, and the q goes away. And so now we can say this constant c that we wanted to find is, is that right? Yeah, 4 pi k. And actually, this is defined as 1 over epsilon naught. Epsilon naught is a constant called the, oh my god, I've been talking a long time. I hope you pause to get a break or drink of water or something. Okay, so epsilon naught is the permittivity of free space. Okay, so epsilon naught is the permittivity of free space, is what it's called. And it is equal to, first of all, it is equal to, you can tell from this obviously, it's equal to 1 over 4 pi times k, which is Coulomb's constant, right? This k we've been using all along as Coulomb's constant, okay? 99. And that happens to be equal to 8.85, no, not 4, sorry. 8.85 times 10 to the minus 12. And the units on it are the inverse of the units for Coulomb's constant. So I believe that makes it, that must make it Coulomb squared per Newton meter squared. Okay. Well, I hope that's right. Let's see. Yeah, I think that's right. Check on that if you want to be sure. But this is the permittivity of free space. It's a universal constant. It's another one of these constants we will always give you if you need it. So don't spend any time trying to memorize it or anything like that. But this is how we use it. We use it for these Gauss's law things. And so finally, we can take this back up. So remember this 1 over epsilon naught was our c. We can take this back up now and actually write Gauss's law in its real form. Okay, so now the c is actually 1 over epsilon naught. So I'm going to do some prettying up here and get rid of that, and then move this up to here, and then this is all over epsilon naught. Okay, so then let me move my pink letters. The charge inside the surface is actually this. Is actually, hang on, let me find it. This. And then the other thing is our permittivity constant. Okay. Permittivity of free space is this guy. Epsilon naught equals 8.85 times 10 to the minus 12 in SI units. Okay, and so this here, this in green, that I'm boxing green, is Gauss's law. And so it says for any closed surface, if you can find the total flux through that closed surface, okay, whoops, that's what this phi E is, then that is equal to the total charge inside divided by epsilon naught, which is this constant here. Okay, another version, you could turn the epsilon naught into 1 over 4 pi k, but we're going to leave that alone for now. So that's Gauss's law, and if I have time, I'll do one or two more showing other common geometries to give you a feel for how it's used.